Hello students, welcome to the third part of noise analysis video series. In this part, we'll discuss about the properties of power spectral density and variance. So before we jump on to this properties, we'll have a quick revision of what we have done in the previous video. So we discussed about power spectral density of a random process, which is x of t. Now, one could represent the power spectral density of this random process x of t as s suffix x of f. Now, in case if this random process x of t is representing a voltage, say for example v of t, then one could represent the power spectral density of this voltage source by SV of f and has a unit of volt square per hertz. Now, in case if this random process x of t is representing a current source, then accordingly the power spectral density would then represent it as S suffix I of f, and this will have a unit of ampere square per hertz. So basically the power spectral density is a quantity that belongs to the frequency domain. We also discussed about Wiener-Kirchhoff theorem, which helped us to convert this power spectral density into an autocorrelation function. Now, for a noise which is a stationary random process, this autocorrelation function has a non-zero value only at tau that is equal to 0, and due to which the autocorrelation function has got simplified to this simple integral. Now that when this integral is run from minus infinity to plus infinity over the entire frequency band, then the autocorrelation function would then represent the total average power, and in short we can write it as P total. Now, in case if this integral is not running from minus infinity to plus infinity, but rather it is being restricted only to a specific band of frequency, say for example between f2 to f1, then this autocorrelation function would then represents the average power or the variance, or it also represents the mean square value. Now, the way we distinguish the average power, variance, or the mean square value from the total power is by using something like Vn square the whole bar. In case if we are discussing about a voltage source, or it can also be represented as In square the whole bar in case we are discussing about a current source noise. The moment if the power spectral density becomes a constant where it doesn't depend on any frequency, then this integral will then step down to a very simple relation. And sorry for this df which is not here. Okay, yeah. So the integral that runs between f1 to f2 would then turns out to be a difference of f2 minus f1, and that is what is being represented in terms of delta f. Okay, so this is possible only when I have a constant power spectral density term. So now we just move on to the properties of power spectral density and variance. Here we will discuss about three important properties of power spectral density and variance. The first two among the three are the properties that are related to the power spectral density, and the last one is a property that belongs to the variance. So as you know, the power spectral density discusses about the frequency domain characteristics of a noise, whereas the variance represents the time domain parameter of a noise. Hope that you're clear. So now we'll just begin with the first important property, which is known as the spectrum shaping by transfer function. Now, it's basically a theorem from the communication system course that you would have learned in the previous semesters. So in this case, consider that we have a signal x with a power spectral density denoted with S suffix x of f, and that when it is being applied to a linear time invariant system having a transfer function h of f, then the output power spectral density of this system can be written simply as a product of magnitude square of the transfer function times the input signal power spectral density. So you have to be aware that it is not just a simple multiplication of power spectral density with respect to the transfer function, but we have to take the square of this transfer function. The reason here is that since we are dealing with the powers of input and output signal, the transfer function of this LTI system would then be represented in terms of modulo square. Okay, so let us illustrate this phenomena with an example. Let us consider that we have a white spectrum across the signal X, which has been fed to a system having a transfer function which looks something like a weird shape here. Now this could be a kind of bandpass filter that we have as a transfer function for our LTI system. So now if this power spectral density is multiplied with the transfer function square of the LTI system, then the output of this would then look something like this. Okay, so this is the reason why it is termed as spectrum shaping. Clearly the input had a white spectrum and that has got molded into the shape of this transfer function at its output. Next we discuss about frequency folding, which is again a parameter with respect to the power spectral density. Consider a power spectral density having a double-sided spectrum centered around this DC component. Now one could remove one of the frequency component just by folding this onto the other side. So when we do so, you could able to see clearly that the magnitude of this one-sided spectrum would then get doubled when compared to the two-sided spectrum here. Now let us see how one could use this folding technique in calculating the total power of the signal x of t. So let us try to calculate the power between the frequency f1 to f2. This power is nothing but is an integral over this set of frequency in the negative axis and plus the integral over the positive axis between f1 to f2. Now one could use the folding technique to just consider only the positive side of the frequency spectrum. So that would result in a quantity which could be written as twice the spectrum that we have on the positive side of our frequency spectrum. And the third important property which belongs to the variance is the summation of noise power. Consider a circuit that has many different noise sources, and these noise sources are independent of each other. Now that you have calculated the noise contribution because of these individual noise component inside the circuit as P average 1, P average 2 and so on, and in order to calculate the total average power, what one could do is by adding these powers. Okay, so you have to be clear that in order to compute the total average power due to various noise component, one has to add the power terms, not the current source terms or the voltage source terms that are responsible for these average powers. Okay, so this becomes clear as we move on to the next video. So these are the three important properties that one has to remember in the next couple of lectures. Thank you.